Our next speaker is Carlos Florensa, who will tell us about unsupervised learning of image embedding for continuous control.
Thank you. Yeah, this is work done this summer at DeepMind with some fantastic people, Jonas, Niklas, Toby, and Martin. The main motivation is that supervision is expensive. Rewards that are very often just given for granted in reinforcement learning, in the real, in many settings, might require considerable engineering. We have here to the left a detector of whether two Lego blocks are stacked, and these took substantial effort to be able to avoid like false positive and so on. In general, to know what's the position of objects, we might require instrumentation of the environment, like here the AR tags, or some of the works that we have been seeing from OpenAI with an awful lot of markers and 12 cameras around. So the idea would be, what can we do to learn with uncalibrated sensory inputs just from images, no positions and no external rewards? This would be the motivation. And the dream would be to learn this policy, that is a policy condition on a goal observation, and our robot just gets in the observation of the world in the current state, and it knows how to take action such that it reaches the observation that we're giving it. And we're gonna see, now the question is, what signal should we use to learn this policy here? But again, assuming that we don't have access to rewards, external rewards, right? We can still use as signal the distance in pixel space because, well, we have the images. But this is a very noisy distance, and it won't give us a very interesting signal to learn. You can try it. It won't be very great. You can also, there's some recent work done actually by Sergey that uses a distance in an encoded space. In their case, they learn a VAE, and then they use the distance in the encoded space. The only issue with this is that it may be prone to aliasing because this embedding space is just learned on encoding a bunch of images, and it doesn't really know about how to reach from one image to another and so on. So it might be prone to aliasing. Then one thing that would avoid both would be if we could use the indicator reward, meaning of like exactly matching the observation. These are very unpractical reward, but bear with me for one more slide, and after we'll deal of how to use this reward. First of all, let's look at what the optimality Bellman equation looks like for this indicator reward. This is not something new, but it's very interesting, I think. Here we have our indicator reward that is given if we exactly match the observation. And if we don't match it, well, we have the Q at the next answer, right? The max of that. Let's look at one trajectory. Here we are at this current observation, and let's imagine for one moment that the goal was exactly one step ahead. If we look at the equation that we have above here, the optimality Bellman equation, we'll see that the Q actually should be 1. It should be this term here, and the rest should be 0. So you can also write it as gamma to the 0, gamma being the discount factor. Instead, if the goal was 2 steps ahead, the first term would be 0, but then the second term, we know that this one should be 1, because we know that there's one action that leads us to this goal, which is the action that we took from here to here. Finally, if you keep recursing this logic, you'll see that if the goal happens to be in this trajectory h plus 1 time steps ahead, your Q at the current step would basically be at least gamma to the h. The lesser than or equal basically corresponds to the fact that if there's a shortcut, this max here will ensure that you actually take the shortcut, right? So we can see that there's a special structure here in the Q, and we'll later on propose something to make use of it, a special structure to make use of it. But first, let's look like in practice, how do we deal with this reward? The first thing to do is, well, to obtain this indicator reward, to be able to observe it, we need to relabel the trajectories that we have in the replay, such as states that we have visited, we consider them now as goals. This is exactly the idea using hindsight experience replay. And like this, we can observe this reward actually as often as we want. On top of that, to propagate the reward faster, we can feed the Q function with an algorithm like retrace. And to maintain a high entropy policy, we can use maximum posteriori optimization to update the policy. Those are just the details of the algorithm. And finally, here, another the main contribution that we have would be to leverage this minimum distance property of the Q that I introduced before to propose a better structure for the Q, and we'll see that we learn better with that. Standard unstructured Q function would take the current observation, the goal observation, embed them, possibly with different embeddings, and then just concatenate everything together with the action and give us the Q. Instead, what we propose is to use a structured cube function that embeds the observation, the current observation and the goal in the same embedding. That's also done with other things. But like the interesting thing is that now the Q will be forced to have this shape of gamma to the, and in the exponent we'll have here the distance and the Euclidean distance between the embedded current observation and the embedded goal observation. On top of that, we need to add the action. And for that, we decided to only add the action around the embedded current observation. And here you have the action. This particular structure gives us a very interesting connection with model-based learning. In particular, if you remember this equation that we were imposing when we're having the goal that is exactly 1 time step away, which we can do with inside experience replay. And now if you remember the exponent that we just proposed, it's basically the same thing, saying that this norm should be 0, and therefore this f becomes a model in the embedding space. To see this pictorically, we have this observation, and this action takes us to this next observation, and we plot here the embedded observations. We can see that this f just becomes, when it takes the current action, it just becomes a dynamics model in this latent space. Let's look at the experimental question first. Well, does this structure in the queue help in the learning? And is this embedding interpretable? And we'll see this in 3 simple Mujoko tasks. There are point mass, navigating around, having an obstacle, or a 7 degrees of freedom J arm trying to feed the position. The first baseline will be the unstructured queue, the one that I introduced before, that has no distance structure or anything. The shared encoding is exactly the same one, but the 2 vision stacks are the same. And finally, the structured queue, which is the one we propose, uses the same vision stack and also has this special structure that I introduced before. This is the results in the point mass. Down is better because this is the final distance to the goal in state space, so which is something we do not use for learning, but we do use for evaluation. And we can see that the structured queue learns much faster and the asymptotics also better. The same happens with all the other tasks that we tried. Then let's quickly analyze the embedding. So if this is the current observation where we start, and this is the goal observation that we want to reach, a trained policy after 2 seconds would go half of the way, and after 8 seconds will already be around the goal. And let's color code those such that, for example, if we look at the evolution of the distance in pixel space, we can see that it's very noisy, and it has no idea that it's getting closer to the goal, or that it's even hard to say that, well, this is the level where you're at the goal. It's very hard to say. Whereas if you look at the distance in our embedding space, this is with the exponent, but you clearly see that it knows that it's getting closer to the goal, and it does converge to like 0.9 something, which is basically means that it knows that it's only a few actions away from the goal. It's never exactly 1, which is what would be because you never actually match the observation that you're given. But it knows that it's very close. We can visualize the policy, for example, for the JCO arm, that to the right you have the goal image, and to the left you have the policy. And finally, let me wrap up with some takeaways. We have introduced no reward learning of visual goal reaching. We have introduced a structure of the queue function that improves performance, and we have connected these with model-based. We haven't leveraged that heavily, but it will be interesting to continue work on that, for example, using it for planning and so on. And with this, I want to thank you and come to the poster if you have more questions.
Thank you. Yeah, any questions?
So are you also learning the embedding along with all of the whole model, and what's the sample efficiency of this algorithm if you do that?
Yeah, so the interesting point is that the embedding is not learned on the side. It's the same, like the only updates that you're doing are the learning the queue function and the policy, right? So you're using your standard queue learning algorithm. In this case, we use retrace to feed the queue function, and maximum posterior optimization, policy optimization to learn the policy, which is like standard reinforcement learning algorithm. And this gives you this embedding that the distance in this embedding space is related to the minimum distance, the minimum number of actions that you have. So it is not learned on the side.
I see.
This avoids the problem that I was mentioning before when you train, for example, a VAE to have like this embedding space and give distance rewards as distance in this space. This is not really related to your task, so you can have like aliasing and these kind of things. So yeah, there's no parallel process. It's all done with your standard queue.
But like, how many samples are you using typically to train these models?
Yeah, so in the cases that I was showing before, it's like a few million steps in the environment.
Okay.
Yeah.
maybe one last question. All right, let's thank the speaker again.